Good afternoon. Now we are going to see unit 1 we have already seen, unit 2 also we have seen, and now we will go to unit number 3. So just stresses, then relationship, determinate, indeterminate, temperature stresses, SFD, BMD, cantilever, SFD, BMD, simply supported. And now switch over to the bending stress. Now question will be write down formula for bending stress. Do not confused with this. We have formula sigma is equal to m by I into y. Now we know what is sigma. Sigma is bending stress. Bending stress. M bending moment. Unit of bending stress, all units are Newton per mm square. Or if we ask what is Pascal, then we know Pascal is nothing but Newton per meter square. M, we have bending moment. Unit you should know. So we have bending moment. What is unit? So we have Newton millimeter because moment is force into distance. I, moment of inertia. You should know all these terms. Moment of inertia. Unit of this, millimeter to the 4, meter to the 4. So that is dimension to the 4. And why? This is most important term. Distance of the fiber from neutral axis. Distance of fiber from neutral axis. And as it is, if I will draw a diagram, then we are in this fashion. Y is measured from neutral axis. So what is y of value of y of neutral axis? Y is equal to 0 at neutral axis. What is neutral axis? It is the axis at which neutral axis or plane where stress is 0. Above this, we have compression or tension, means we have opposite nature of stresses below and above neutral axis. It is the boundary which differentiate your compressive and tensile stresses. So bending stress is always 0 at neutral axis because y is always measured from neutral axis. Measured from neutral axis. And then which is maximum distance from neutral axis? So topmost and bottommost, these are the distances which are maximum from neutral axis. So we have sigma max at topmost or at bottommost fiber. Because this is y max. Y max. This is y max. One is in compression, another is in tension. Now we have m by I constant for a bending moment diagram. And therefore, sigma is directly proportional to y. And we have bending stress diagram always linear. Bending stress diagram is always linear. And therefore, we have these as two triangles, one compression, another tension. So this is most important statement. Units, bending moment, Newton millimeter. I millimeter 4. What is unit of Y? Is millimeters. So in bending stresses, we have to keep formula and all the terms we should know with units. Now we will go with rectangle. We will draw bending stress diagram. We have in this way. Then we have circular section bending stress diagram in this way. We have T section bending stress diagram in this way. We have I section in this way. We have unsymmetrical I section in this way. What does it mean? Bending stress diagram is independent of cross section. Bending stress diagram is independent of cross section. Independent of cross section, or bending stress diagram is same for all cross section. Bending stress diagram is same for all cross sections. All cross sections. So we have this rectangle, we have circle, we have T section, we have I section, we have unsymmetrical I, this is symmetrical I. Then also our bending stress diagram is not going to change. It will remain as it is. And this is most important statements. So keep it in mind these statements. You have to write all these, you have to draw the diagram and upload it. So we have shear stress diagram. Now I will write formula. Tau is equal to VAY bar upon IB. Now I will write values terms one by one. Tau we have shear stress. Unit we have all stresses. Unit is same. Stress we have Newton per mm square. Unit of V, what is V? We have shear force. What is unit of V? We have Newton, we have kilonewton, likewise. Then I, we have same, millimeter to the power 4. Then we have B, this is width at the section where stress is calculating. Now what is VAY bar? AY bar. So now I will draw the diagram of I section. So we have neutral axis over here. And then we will plot I. So now what is AY bar? AY bar is moment of area. Moment of area. Moment of area. Moment of area above or below. Just a minute. So we have above or below. Means if point is above neutral axis, then we have to take area above it. If point is below neutral axis, point above neutral axis, consider area above it. If point below neutral axis, then consider area below it. Moment about neutral axis. About neutral axis. So now try to understand this. So if we will consider this section, then what is AY bar? So I have to consider this area. So let us, we have width is B and this distance is Y. So what is area? So we have area is B into Y. And then we have to find distance of the centroid of this area from neutral axis. That means we have to consider center of this, and from this we have to consider y bar. You should be in position to explain to external examiner. And so by into y bar. Now this is Abu. Suppose you have taken area below neutral axis. Then we have to consider this area. So let us, we have this is B and this is Y1. So we have area equal to B into Y1. And now, because point is below the neutral axis and we have to consider area below it. So at this point, we have to find shear stress. So this is below neutral axis. So we have to consider area below it. So we have considered this area. And now y bar, we have from this. So I will write it as y1 bar. So we have this as y1 bar. So likewise, we have to consider these values. A is by bar and ay bar. Sorry, this is ay bar and this is also ay bar. So ay bar. So ay bar. Area we have by1. Here area is by and this is y bar distance. That is from neutral axis. So what will happen in this case? We have topmost point. This is topmost point. It is above neutral axis. So area above it. So we have A0 above this. And therefore we have tau 0 at topmost. If we will consider this point, here we are interested to find shear stress. It is below neutral axis. And we have to consider the area below it. Below it, we have area 0. So my value of tau is 0. And therefore, shear stress is 0 at topmost point and bottommost point. And bottommost point. Bottommost point. So this is most important where you have value of shear stress 0. Bending stress 0 at neutral axis. Bending stress 0 at neutral axis. But here shear stress is 0 at topmost and bottommost point. So this you have to keep in mind. Then where we have maximum, so you can consider, if I will consider neutral axis point. So if I will draw diagram on this side. And this is neutral axis. So we have maximum area to be considered when we have at neutral axis. And therefore, maximum value we will get at neutral axis, because in that case, we have to consider maximum area that may be of above or it may be considered as below. So at neutral axis, you can consider upper area of neutral axis, or you can consider bottom area of neutral axis. You will get same answer. But tau max we have at neutral axis where my bending stress is 0. And if we will draw the diagram of bending stress and shear stress for a rectangular section at a glance, then you have in this way. So I have bending stress diagram. I already mentioned we have bending stress 0 at neutral axis and maximum at topmost and bottommost point. So we have like this. So this is bending stress. Bending stress. And then we have shear stress. And we are already mentioned shear stress we have 0 at topmost and bottommost. And we have maximum at neutral axis. So diagram will be in this fashion. So we have maximum at neutral axis. And here we have maximum at topmost and bottommost point, 0 at neutral axis in shear stress, 0 at topmost and bottommost point. So this is shear stress. And this is most important. Shear stress is not shear stress depends upon shear stress depends upon the cross section, because in formula we have A over there, and therefore we have different shear stress diagram for different cross sections. Whereas if you will see formula for bending stresses, M by I into Y, no A is there, and therefore we have this as same for all. Now then we have next shear stress diagram. We have formula, if you will see, we have formula that is VA y bar upon IB. So I can write it tau VY y bar upon IB. And this is constant part, and therefore we have tau directly proportional to y bar. So this is square of vertical distance, and therefore you will get parabola for shear stress diagram. SP, I already mentioned, remember SP, shear stress parabolic. Shear stress parabolic, you have to keep in mind. So now we have next, I will consider different section. So we have, this is rectangular section, and in rectangular section we have this value. Try to understand. We have shear stress diagram, maximum at neutral axis. We have 0 at top and bottom. Never forget this. Then you have circular section, symmetrical. Again you have 0 at top, we have 0 at bottom, maximum at neutral axis. Then we have T sections. So now try to understand. If I will draw a neutral axis, then we have somewhere here neutral axis. And then you can see we have value in this fashion. So this will be suddenly changed because your value of B and value of this B win, whatever ratio you have, B upon B win, you have to multiply this value of straight by this ratio. So we have likewise. So at junction, we have two values of B. One is of flange, another is of web. And ratio of this will gives you a ratio of this stress and this stress. Then we know we have maximum at neutral axis and 0 at bottommost. So we have, this will be shear stress diagram for T section. You should be in position to draw all shear stress diagram. Keep in mind. Then we have I section. Then we have at this. Then we are in this fashion. Neutral axis, maximum. Then we are in this fashion. Now you have to keep in mind. If I have symmetrical section, then my values, these are same, and these are along this same line. These are along the same line because we have symmetrical. So we have this diagram symmetric with neutral axis. If I have unsymmetrical section, then we are in this fashion. Now you can see your values are not one after another. So we are in this fashion. Then we have, this will be changed. So these are also not along the same line. You can see this. We are like this. So not along the same line. And then in this way. So this is not symmetrical with neutral axis. Now what will be the value which will go inside, outside? I have not considered that one. Simply I have drawn it to see the changes between the two. So we have to draw a diagram in this fashion for shear stress. So formula, so again, bending stress linear, bending stress diagram linear, 0 at neutral axis, maximum top and bottom. Top or bottom I will write. Top or bottom. If you will go to shear stress diagram, then already we have seen shear stress, we have shear stress 0 at top and bottom and maximum at neutral axis. And maximum at neutral axis. Only some exceptions are there. In triangle don't have maximum at neutral axis. Don't have tau max at neutral axis. So we have some very rare cases we have where we do not have maximum at neutral axis. So likewise, you have to keep in mind all shear stress diagram. And that is shear stress diagram for different section, and bending moment diagram we have same for all. Now we will stop here only. Thank you.